Okay, so let's start. So I want to remind you first what we did last time. So we did two things. One is we briefly went over semi-supervised learning, and I want to leave with you two options that we discussed briefly. And the reason is that it's going to be important and help you understand what we're doing at the rest of today. So if you remember, the scenario that we had was we had a bunch of supervised examples, and we trained a naive Bayes algorithm. Right? So basically, by training a naive Bayes algorithm, we kind of had this picture here. Right? So we trained, we collected statistics for the V options, the V label, and for the N label. And then we asked the question, okay, so now we are given new examples or that are unlabeled. And the question is, what do we do with it? And you basically suggested two options. So one option was we can we have a model now, right? We learned the model from these 10 examples. We can use this model to make predictions on all the unlabeled examples. So this is option one. And once we made predictions on them, we can assume that we have labeled data and keep on working as if we have labeled data. Option two was do almost the same, also use your model to predict on the unlabeled examples, but don't quite make a prediction, but rather retain the uncertainty. That is, if your model tells you that this is a probability, that this is an N example with some probability and a V example with some probability, keep these two labels and keep the distribution over them. Right? So every example now actually does not have a label, but rather has two fractional labels. With some probability it's N, with some probability it's V. And again, we said, if we have this option, we can keep on going and train our algorithm using this way, right? So it's essentially, instead of having a data set that has labeled data, where each example comes with either 1 or 0, we have a data set where each example comes with a little bit of 1 and a little bit of 0, or in this case, a little bit of N and a little bit of V. Right? So these were the two options, and we can go ahead with it. So that was the unsupervised, the semi-supervised case, and I want to just keep this option in your mind because it's going to be, it's going to help you when we move to the next algorithm. Yeah. Sometimes you can, sometimes you cannot. Okay, good. So you can just, so let's say your examples are bit vector of dimensionality 100, and you can just generate bit vectors of 100 bits. What's the problem with this? Yeah. So, but you want to generate unlabeled examples, right? So unlabeled examples, I can always write unlabeled examples in this space. Still, what's the problem with this? In general, these could be even illegitimate examples under some definition of legitimacy. So think about this example here. In the examples here, bit vectors, examples came from a specific model, right? They represent sentences, right? I gave you these, where was it? Okay, here. Sentences. Now, if you just generate bit vectors, it's not clear that there exists a sentence that could have generated this bit vector. So what you generate is just random things. You learn over random data. Then when I test you on some real data, unclear that what you've learned has any relevance to this, right? So everything we're saying in learning theory, there is some notion of a distribution, and everything works only because there exists some notion of a distribution that generates the data in training and will generate the data in test, right? So we have these two issues here. First of all, you may generate illegitimate examples relative to the domain, and two, who knows where they're coming from. So the only reason learning works is because of the consistency of distribution. The only reason unsupervised or semi-supervised, as we are going to talk about today, work is because the distribution is real. It really represents something, and it has some regularities that we're going to exploit in our algorithm. So just generating random things is not going to help. Either yes or not. I don't know. So if people tell you, I want to learn a conjunction, again, recall the analysis that we did for Occam's razor for conjunctions. What was the basic idea in this analysis? We said we've never seen an example where x6, it was, I think, was on a positive example. And we're going to rely on that to make an argument that it's going to be okay. The fact that we did not eliminate it from the conjunction is going to be okay, because if we haven't seen it in training, the likelihood we're going to see it in test is going to be small. So this was the basis for analysis, and the basis for Occam's razor, the basis for all generalization. Right. Right. So your protocol now is you want to learn conjunctions in an unsupervised way? So let's... So if you know nothing and I give you no labels, without any distributional assumption, you will learn nothing. Right? Again, let's go back to the examples that we started the class with. I'm going to give you some examples. I'm going to look at what labels you assign to them in your learning algorithm. And now I'm going to make sure that nothing is going to be consistent with what you've learned, because you give me complete flexibility. All right? So we always rely on the fact that there is some regularity. Okay, so this is really an important thing. Again, what I wanted now is to plant these two options in your mind. And once it's there, let's move on to the coin problems. Okay, so we ended by looking at coins. We had three coins. Coin 0, coin 1, coin 2, and we looked at three settings. The first setting was we toss, actually I changed this to 4, but I didn't change the 6 to 4, so we toss one of the coins 4 times, scenario 1, and then I'm asking you, let's assume I tell you the P and the Q, the values. Can you tell me which of these coins is more likely? And the answer hopefully is yes, you can do it, right? Because you see that here your most likely estimation is going to be 3/4, and you just choose P or Q depending on which one is closer to 3/4. Question 1. Question 2 was, first we toss coin 0. Given the outcome of this toss, I'm deciding whether to toss coin 1 or to toss coin 2. But I'm recording the toss of coin 0. It came out head here, tail here, head, and head. Given this scenario, hopefully, you can easily estimate the most likely value for P and also for alpha. P, Q, and alpha. Agreed? Okay, so the interesting scenario then is scenario 3, where I do the same thing, but I do not reveal what was the outcome of the 0-coin toss. So you see a sequence of coin tosses, but you don't know whether it came from the P coin or the Q coin, the first coin or the second coin, and you want to estimate, nevertheless, the parameters, and you also want to estimate alpha. And okay, so we really, this is the model that we have here, where, first of all, I choose the toss of coin 0, and depending on its value, I'm tossing one of the coins n times, 4 times in this case. And as I said last time, there's actually, the interesting thing is that there's no non-analytical solution to this problem, but we're going to figure out an algorithm which is called the EM algorithm. So here's the key intuition that we want to develop here. So really, if we knew which of the data points came from coin 1 and which came from coin 2, there was no problem, right? You look at the at this HHHT, I would tell you it came from coin 1, you have an estimate for P, right? And the same thing for each one of them. The problem, of course, is, and you know how to do it, right? So this is just a reminder. Once I tell you the label, you just do the maximum likelihood estimate. We did this. It's basically K over M. Here we don't have it. So instead, what we're going to do is we're going to use an iterative approach that goes like this. So we're going to guess the probability that a given data point came from coin 1. 1 minus it, in this case, is going to be the probability that it came from coin 2. With this guess, we're going to estimate the probabilities. Basically, we're going to compute the most likely value of the parameters. And this is exactly the naive-based problem that we talked about before, right? So once you know the labels, and it doesn't matter whether the labels are real labels, 0, 1, or fractional labels, a little bit n and a little bit v, you can compute the most likely value of the parameters. Now you have a model, you have parameters, you can compute the likelihood of the data and re-estimate the parameters again. And this basically is going to be the algorithm. This algorithm is called expectation maximization for a reason that you will see in a minute. And this algorithm is good in the sense that if we made the right assumptions on the probability distribution or the family of probability distribution that generated the data, it can be shown to converge to a local maximum of the likelihood function. So now let's give the details. So really, this is the game that we're playing here, right? So if we have labels, we can find model parameters. If we have model parameters, we can think about them as giving us labels or fractional labels. And this game allows us, is driven by maximizing the likelihood of the data. Okay, so now let's start doing this work. So as I said, we're assuming for a minute that we know the parameters. So we know P, Q, and alpha, or an estimate for P, Q, and alpha. Given this, I want to know, okay, so what's the probability that this sequence came from coin 1? And we can compute it. This is my notation, just that you'll remember. So we have n data points. In each data point, we have m tosses, out of which hi, sometimes I just call it h if it's clear, are heads. Okay, so, and my assumption is that I know P, Q, and alpha. So how do I write down the probability that a given data point came from P1? It's basically this. I'm going to denote it P1i. Data point I came from 1. It's the probability that it's coin 1 given the data. Using Bayes' rule, P of D given coin times P of coin divided by P of D. And we know how to compute it. So the probability that it's coin 1 is alpha. Given that it's coin 1, the probability of observing this data, that means H heads and M minus H tails is this, because it's the P coin. And then I'm dividing by the probability of the data, which is just a normalization, right? So it's either came from coin 1 or it came from coin 2. So that's the probability of the data. Okay, so I have an expression which I'm calling here the estimation, or later it's going to be the expectation step, for estimating the label. Right? Exactly like before, estimating N or V. Now that I have this, I'd like to compute the likelihood of the data and find the parameters that maximize it. So we're going to maximize the log likelihood of the data. This is the log likelihood of the data. Sum over all data points, log of the probability of the data given the parameters. Now, we don't know all the data, so we marginalize over the name of the coin, which in this case I'm writing as, so it's log, sum over the name of the coin, P of D, comma, the name of the coin. So in principle, we know what we want to do, but this problem turns out to be hard. It turns out to be hard because the log is inside. So what we're going to do here, and we can give two explanations for it. So this explanation is a little bit weak. I'm going to show it in a more formal way a little bit later. But basically, since this y is not observed, we really can't use the complete data log likelihood, which is these things. Instead, what we're going to do is we're going to maximize the expectation of this thing. We kind of think about this expression as a random variable that depends on y, the hidden value. And instead of maximizing the log likelihood, we maximize the expectation of this random variable over the coin's name. Now, in fact, this can be justified, and I'll show it a little bit later, by really moving to an upper bound of this log likelihood using Jensen inequality. I actually write it here, but I'm going to show it in a more formal way a little bit later. But basically now, if we agree that instead of maximizing the log likelihood, we're going to maximize the expectation of the log likelihood over the values of the hidden variable, that's what we have, right? So we have this expected log likelihood, which is basically the expectation of this, which I had before. And I'm just writing down the expectation. So it's the sum over the probability of d, comma 1. Here I have d, comma 0. And these are the probability of seeing 1 or seeing 0, right? So basically, all I used is just the definition of random variable, right? So this is the random variable. And the value it can take is either this, with probability P1i, which I computed before, or this with probability 1 minus P1. So all I need to do now is just plug this in, and I'm going to compute it here. So this is the expectation I care about. I'm writing it as this sum, P1 times log this probability, 1 minus P1 times log of this probability. Now, we know how to compute these probabilities. So this probability is alpha P to the H, 1 minus P to the M minus H. Here it's the same thing with the Q's. I'm computing the log now, so I'm getting this linear sum, and that's it. Now the question for me is, okay, so you have an expression for the expected log likelihood. Let's find the parameters that maximize it, and we know how to do it. We're going to differentiate relative to the parameters. So let's just see what happens. Okay, so before I show you, let's just look at this expression and see what happens. Let's assume what I want to do is I want to find alpha. So notice that this does not depend on alpha. Same here. These do not depend on alpha. So all I get here is differentiate this. The sum is there. So basically, I'm going to get this probability P divided by alpha. From here, I'm going to get 1 minus P divided by 1 minus alpha. So So that's what we get, right? So we get the sum, P over alpha minus, because of this guy, 1 minus P over. And I want to equate this to 0. And this is what we get. With simple algebra, you will see that what you get is that alpha is estimated using the sum of the P1i's divided by n. Let's just see if it makes sense to you. What does this mean? It's the empirical mean. Why is this the empirical mean? No. It doesn't assume any, it doesn't make any assumption of uniformity. Let's take the extreme case. Okay, let's take the case where rather than fractions, what I do is I choose the PI's here, the P1i's are extreme probabilities. So P1 is 1 or 0, for example. So what do I get? Let's assume that all the P1i's are 1s or 0s. So what does this expression mean? It's really the fraction of points, right? So look at all those that are 1 and divide by n. So how many of the data points are labeled 1 divided by the number of data points, right? This is alpha, right? You expect this to be alpha. Just want to make sure that this is a sanity check for you too, right? So if I make all the P1i's for all i's to be either 1 or 0, this essentially count how many points are labeled 1. And we divide by n. Now, so this is just a generalization of it, where I'm not saying that all the P1i's are 1 or 0, but I'm giving them fractions. So still, I'm counting all the head fractions here. I'm summing over all the head fractions and dividing it by n, which is what hopefully you expected to get when you compute alpha, right? Okay, and now the same thing you can do for the P1i, for the P and for the Q. And a little bit of algebra will give you this. And again, you want to do your sanity check. So imagine that all the P1i's, for example, are 1s or 0s, and think about why this makes sense. And it will make sense to you. Okay, so basically we're done, right? So this is the second step of the algorithm. So we had one step where we estimated this P1i using a guess. Once we got this P1i, now we have a new set of parameters, and we can keep on going. Okay, so again, do the sanity check and make sure that it's right. And another thing, just to make sure that we understand what we're doing here. In this step here, I fix P1i. It's a number, right? It's not a function of anything. It's just a number. And I'm computing the parameters, the new set of parameters, as a function of it. So we have an algorithm. Now, we don't know whether the algorithm is good or not. I'm just promising you that it's good, but hopefully the algorithm is clear. Questions? Yeah. Here. No. Oh, you're right. Sorry. This should be Q's. Yeah. What about here? Oh, this was good. Okay. Yeah, here it was good. Yeah. Thanks. Okay, so that's kind of the algorithm. And I want now to, we're going to do one more example of the same algorithm, but I want to now place it in a more general setting. So what are we doing here? Really, we have a model to learn in the presence of hidden variables. We have two sets of variables, let's say x and y here. And we are looking at this joint P of x, comma y, given a set of parameters. We know how to deal with it in the general setting, right? If we observe everything, we just want to maximize the likelihood of the observed data. In this case, we only observe x. We don't observe the y's. So what we are doing is we want to look at this component, log of p of xi given theta, and we're going to write it as we marginalize over the y's, which means sum over all possible y's, p of x comma y. And this is what we're trying to maximize. So the EM algorithm is a method to basically maximize this thing. And we gave it in a very specific example of these binomial distributions over coin. So let's try to do it in a more general way. So because it's, as I said, it's a general purpose algorithm. It's going to find the maximum likelihood, whatever the model is, as long as you know how to write the log likelihood. So the idea is this. In the E step, we're going to fill in the latent variables, just like we did with the P1I, right? So we guessed what the labels are. We guessed what the parameters are, and we use them to complete the labels. The P1Is were our fractional labels. And once we did this, in the M step, we maximize the expected log likelihood with respect to the posterior distribution. So let's just do it now in a general way and see what happens. So my data is going to be this endpoints. Z is the hidden variable. And in the next 3 slides, I'm not committing to any particular model. It's going to be a general setting. And theta is the model parameters. So we care about the theta star, which is the argmax over all possible theta of p of x given theta. And as I said, we're going to marginalize over z. So it's the sum over z of px comma z given theta. I'm writing this using Bayes' rule this way. P of z given theta times p of x given z and theta. Just Bayes' rule. Okay? And this expression is sometimes called the complete log likelihood. I really haven't done anything yet. So we want to derive an algorithm. And as we said, we want to maximize this. And as I showed in the previous example, it's not easy to maximize this as is. So we're going to derive a simpler objective function that we're going to maximize. Basically, the way we're going to do it here, and it's not the only way to do it, is we're first going to multiply it by qz over qz, 1, where qz is just arbitrary distribution over the random variable z. So I'm writing again p of x given theta. This is the stuff I want to maximize, marginalizing it. And here I'm writing it as we did before, p of z given theta, x given z and theta, times qz over qz. Now notice that I can think about this now as an expectation relative to qz. Right? So basically, this is qz times something. So it's an expectation relative to q of this something. And this something is this, p of z given theta, p of x given z and theta, divided by q of z. Okay? Again, I did nothing. The reason I did this is because now I can say that this is always greater than. So what do I have here? I have log of expectation. I can say that this is always larger or not smaller than the expectation of the log. Basically, that's the key thing. Where this is due to Jensen inequality. So Jensen inequality is known to say, is known for convex functions. It says that the expectation of a function is greater than the function of the expectation. Now, we are using it here for log. Log is actually concave rather than convex, so the other thing happens. And just to make sure that you get an intuition, it's actually a very simple thing to show. This is a convex function, right? So I have 2 points, A and B, and I can either look at the average of A and B, which is going to be somewhere here in the middle, or I can look at F and A, F of A and F of B, and their average. So you can see that the average of f of A and f of B is larger than the average, than the fractional value of the average, right? Which is basically what I say here. Now, because we have a convex function, it's just the opposite. Okay? So that's in fact, it's directly from the definition of convex or concave function. Okay, so now that we believe this, we're going to deal with this function, and we're going to call this function the EM objective. And this is what we're going to maximize. So this is another way of writing it, and we actually are not going to use it. I'm just going to write it here because sometimes you'll see it written this way. Basically, all I did is I just opened the log here. So I have expectation of this, expectation minus expectation of this. And this thing is really an entropy thing, if you remember what entropy is. And we'll see it again next week in a slightly different context. But, and you know, as I said, there are several ways of writing it, and it's good for some things. For us today, this is going to be enough. Okay, so what do we have? Once we have this objective function, I claim that we have immediately an algorithm. What is the algorithm? So now we're going to iteratively optimize this function. You can think about it as a gradient ascent algorithm as opposed to gradient descent algorithm, because we want to maximize rather than minimize. So we're going to use this Q. Q is the posterior function that we care about. Remember the label that we had before, P1 I. This is P1 I, right? It's the probability of the value of Z given X and the parameter. So I'm going to plug in this Q. So I have an iterative algorithm. In the T space, I'm going to have my Q of T, which is the posterior in the Tth round, and I have the parameters in the Tth round. Again, think about this as the label of the coin, or the fractional label of the coin, the P1I that we had before. So what do I do? In the E step, I'm computing the Q, and I'm doing it by argmaxing over the Q value of this objective function, which is just computing the posterior, the P1I. And in the M step, I'm going to assume that I got this, and I'm computing the log likelihood. I'm maximizing the log likelihood of the function given the old parameters that I had and the new estimate Qt plus 1. So again, in terms of what we did before, Q was our P1I, theta was the parameter, alpha, P, and Q, and that's what we did. Now, you can also just, again, as a sanity check, you can plug it in, and you will see that you get the right thing. That is, that if you do these things, you're gonna get you maximize what you want to maximize. So I'm just going to write this. This is, again, some algebra. So this was the objective function that we had in the previous slide. It's just the expectation given over Q log of Pz given theta, Px given Z and theta, divided by Q of Z. I'm highlighting Q of Z because I'm going to plug the right Q of Z that we're using in EM here. So I'm plugging the posterior P of Z given X and theta. So all I did here is I just said, okay, this is expectation, which means it's the sum over Z, the probability times this stuff. So I just copied this. If you multiply this, really what you get is P of X comma Z given theta, divided by Q of Z, which I'm substituting to be P of Z given X and theta. So copying this, I'm just multiplying everything by P of X given theta. So here I multiply by P of X given theta, and here I divided by P of X given theta. So when I divide this by P of X given theta, I'm moving to P of Z comma X and theta. So all I did between this and this is multiplying and dividing by P of X given theta. And now again, I'm copying this here. These cancel. So I'm left with P of X given theta. Now this does not depend on Z. So I can take it outside the sum. So I get log P of X comma given theta times sum over all Z of the posterior. This is just 1. So I got this back. So basically what this shows is that with the right Q, what we maximize is the right thing to do. So, so by the way, so this is EM, right? So again, we can fold this back and just look at this. So we have an algorithm. What I showed you is that we derive this algorithm in such a way that it maximizes this objective, which is very related to what you really want to maximize. But we did it with choosing a specific Q. So it turns out, and I'm not going to do anything with it today, but it's possible to show that you can do EM with other Qs. And with different Qs, you're going to get different algorithms. For example, you can choose a Q such that instead of computing this probability here, the probability of the coin being 1 given the data, P1I that we had before, rather than computing the probability, I can just choose the coin that has the higher probability. That is, instead of using fractional things, I'm just going to choose whether it's coin 1 or coin 2. Remember the two options that we started with. We said that we have two algorithms. One algorithm says, I'm going to use the parameters that I have now, label the examples, and really label them. If it's greater than a half, I'm going to say it's label 1. If it's less than a half, I'm going to say it's label 0. That was option 1. Option 2 was keep the fractions. The naive Bayes the EM algorithm is keep the fractions. But I could have a version of this algorithm, and you can get this version by choosing a different Q that says, I don't care about the probability of Z given X and theta. I just want to know what's the label. Choose whether you want to label it coin 1 or coin 2. And then you can keep on going also. So this algorithm is known as truncated EM or sometimes hard EM. The idea is that instead of maintaining probability distribution over the labels, over the values of the missing variables, you're committing to a specific value. And in fact, in practice, a lot of time, even when you read in a paper that people said we used EM, they will use hard EM. They will actually, rather than maintain a probability distribution over the hidden variables, they will actually commit to a value and keep on going. So the only thing from your perspective is to understand that it's the same algorithm modulo this change, right? So the structure of the algorithm is the same. It's completely analogous to what we started with, where we said we have two options. We can either choose N or V, or we can choose a little bit of N and a little bit of V, which is the real EM algorithm. Questions? No questions. Okay, so let's just summarize this algorithm and move to another example. So that's what we said so far, right? So we start with initializing the parameter somehow. In the E step, we use the current set of parameters, the theta old, to find the posterior distribution of the latent variable, this P of Z, given the data and the existing parameters. So this is what we call the expectation, or sometimes the estimation step, right? Once we have this, we know how to compute the likelihood of the data. We basically computed this function that we sometimes call the Q function. And now we are going to argmax this function in the m step and estimate the parameters. So this is, again, a general statement of the algorithm. As we said at the beginning, it's a family of algorithms. Every time you're going to have a different probability distribution to deal with, and you're going to compute these steps in a different way. So let's now move to another example. Okay, before that, let's do a summary. So that's what we are saying. So it's a general procedure. We did it in one case, right? So we did it in the case of a mixture of Bernoulli distributions. The reason I call it a mixture is each coin was a Bernoulli distribution, and then we had the coin 0, the alpha parameter, that was mixing them, was determining whether I'm using the distribution of coin 1 or the distribution of coin 2. That's what we mean by a mixture. It's really important to realize that it depends on a family of probability distribution. And because the update rule, the specific algorithm that you run, how you update your parameters, will depend on this specific family of distribution. And we're going to give you an exercise where what you'll do is you'll do the same thing that I did for the coins or for the next problem, only with a different with a different probability distribution. You'll have to derive the update rule. Now, the algorithm is actually very, very good, especially when you make good assumptions. So you work with the right family of distributions. Even in this case, you start with a guess. Your guess may not be good. So what can be shown, and I did not show it here, is that this is going to converge to a local maximum of the likelihood function, which means that you will not get to the global maximum in general, but if you make multiple restarts, you improve your chances. And I'm going to get back to this point a little bit later. Okay, so the previous example was a mixture of Bernoulli distribution, and now I want to move to another example, another mixture. And what we're going to derive is a k-means algorithm that I assume some of you have heard about. It's really a clustering algorithm. And we are going to derive a soft version of this clustering algorithm, but we'll talk about, for those of you that are familiar with the hard version of the clustering algorithm, how do we get it also from this EM? So this is the problem we have, right? So we're given data points. We know that they are sampled independently from a mixture of normal distribution, k normal distribution. So k is fixed for us. And we know that the means are mu I. So I'm assuming now it's simpler that all of them have the same sigma. So this is kind of what I get. And the question is, eventually you want to make predictions, for example, right? So given a data point, you want to know which mu does it correspond to. Okay, so again, as we did in the case of the coin, notice that if you knew that all the data point came from one single normal distributions with mean mu, it's easy to find the mu. What will the mu be? Just the average of the data points, just like in the head and tail case. But we can actually prove it now, right? So this is the probability distribution that we're assuming. P of x given mu is this normal distribution. Sigma is fixed for us. We get many data points, and I'm going to compute the likelihood of the data given the parameter mu. In fact, I should have divided by this, but it's not going to matter, where we, this is the log likelihood, and this constant here will not matter when I do argmax over this. So in order to maximize it, I'm going to differentiate this. And if you compute the derivative with respect to this, you can see that you get a linear sum here. And if you do a little bit of algebra and get mu out of it, you're going to get the average of the xi's divided by the number of points m. So really the stuff that you know, that the average is you get by this operation, is derived in a principal way using a maximum likelihood criteria, right? So what we've done so far kind of makes sense, at least matches the intuition that you have. Okay, so that's the easy case, right, where we have one single normal distribution, one mean. And now we want to generalize it to the case where we don't know which mean generated each data point, right? So we have k options. So just like in the cone example, the problem is that the data is sampled from a mixture of k normal distribution, and we don't know, given a point, which distribution it came from. So we're going to basically follow exactly the same procedure as we've done before, only with a different probability distribution. So the first thing we want to do is we want to assign a label to the data point, right? So we're going to make an assumption on our parameters, and given these assumptions on the parameters, we're going to compute, okay, so what's the label of this point? Or for each option, each mu i's, what's the probability that this is the mu I of this point? Right? That's what we're doing. So let's compute it. So I'm going to denote by Pij the probability that the ith data point belongs to the jth distribution, came from uj. So just like before, probability of mu j given that I observed xi. Bayes rule, it's p of xi given mu j, p of mu j divided by p of xi. And we can compute it. So first of all, notice that here, again, for simplicity, I'm assuming that p of mu j for all j is 1 over k. Okay, uniform distribution over the Gaussians. So this is 1 over k. And here, this is just, I'm just writing it in a more explicit way. P of x being xi given mu is mu j, divided by the probability of the data, which is just summing over all k. And now we can write it. We know that it's a normal distribution. This is where the specific assumption of which model we're using comes in, and I'm just writing it. So it's e to this power divided by the sum. The only thing that changes here is the mu. Okay? So I have an expression for Pij, completely analogous to the P1i from before. Okay, so now I'm going to introduce some notation because it's going to be easier. So I'm going to introduce the notation of this Z1i up to Z1k. So Zij is going to be a Boolean random variable that is 1 if xi came from the jth distribution, if xi came from zj. Okay, very simple thing. The reason I'm going to do it is exactly the same thing that we've introduced these kind of variables in the naive Bayes case. I want to write the expression for the likelihood of the data, but I don't know which probability to write down because I don't know where is it coming from. So I'm going to introduce this set of variables. We know that at a given time, only one of them is 1 and the rest are 0, right? Because a given point xi came from one of the j's, cannot come from several of them. Okay, so with this notation, notice also that the expectation of these zij's is Pij, right? It's just a Boolean variable, so we know that E of Zij is always Pij, and if you want to prove it to yourself, this is why. By definition of the expectation, this variable takes two values, either 1 or 0. It takes 1 with the probability Pij, 0 otherwise. So it's just Pij, okay? So that's, so now I can write the likelihood. So this is what we want to write. We want to write what's the probability of all the data. In this case, I'm writing it as xi and all the z's. So basically, it's the data and the hidden variables. The zi's really are the hidden variables that I have, given my parameters. So h here stands for all my parameters. And notice that now I can write it this way. Again, look at what happens here. Basically, what I did is I multiplied all these things. Only one of them is going to be 1 at a given time. So I didn't do anything. I just wrote this big expression because I didn't know which one is going to be 1. That's fine? Okay. So now that we have this, we can compute the log of these things. The log of these things, again, I'm omitting this guy, and I have just the sum of the exponents here, which is what I write here. The expectation of this, which is what we want to maximize in EM, can be written as the expectation of the sum, which is equivalent to the sum of the expectation. So I push the expectation inside. Expectation is linear, so I can push the expectation inside the sum. So that's what I get. I have sum over some constants, sum over the j's of the expected value of this guy, xi minus uj. So I have an expression for the expected log likelihood, and basically I'm done. All I need to do now is I need to differentiate it and figure out what's going to be the values of the mu j. So that's what we're going to do. So we're going to differentiate this function. This is the one that I had here, relative to the mu j's. Very easy to see here that what you're going to get, some constant. I don't care about the 2 that goes there and this one goes there. We don't care about this constant. And I have sum of the E zij's xi minus mu j. And I want this to be 0. It's easy to see that what you get is that mu j is this fraction. And again, let's think about what does it mean. You should be able to convince yourself that this is what you should have seen. In exactly the same way we did before. Right? So the EIJs here are PIJs, right? The probability that the data point xi came from min j. And each data point could have k different probabilities. The probability that it came from mu1, mu2, up to mu k. Let's assume, just for a second, that these PIJs are always 1 or 0. Okay? So under this assumption, basically, what am I doing here? For the case of mu j, I'm counting how many points came from the j distribution, right? I'm counting how many times it's 1. All the rest are zeros, which is what you would have done had I asked you to do it, right? So you basically want to count how many points came from this, divide by the total number of points that are there, and so on. So the only thing we're doing here is we are generalizing it to the fractional case, where only parts of each example came from J, and the rest came from others. Is this clear? Okay, so okay, this is the summary of the algorithm, right? So this is what we did, right? So we guessed parameters. We assumed some u's. Given these parameters, we computed most likely labels. Right? So now I have a parameter. So I'm looking at the point x, and I'm asking, okay, so what's the probability that it came from mu1, came from mu2, came from uk? And this is how we did it, right? Pij is this. Once we have these labels, or fractional labels, we can compute a new set of means. Now, two questions. First of all, people that are familiar with k-means. Is this how you run k-means? Who knows about k-means here? Okay, so how do you run k-means in the standard way? Yes, you decide on k. Right. Right. Excellent. So let me just say it again. Of course, we chose k. We fixed k here. We guess means. K means mu1 up mu k. Once we have this, for each data point, we assign one of the means to it. Basically, we say this data point came from this normal distribution. This data point came from this one, and so on. We assign a distribution in a hard way. So now we have a split of the data. Each subset of the data belongs to one of the means, and we recompute the means. How do we recompute the means? We just average, right? Just how we started. What's the difference between this, the algorithm on the board, and what I just said? Yeah? So that's exactly option 1 and option 2 from the beginning of the class, right? So the standard k-means algorithm is a truncated EM algorithm. Basically what it does, it guesses the mu's, and instead of Pij be fractional, which means each example I could be a little bit mu1, a little bit mu2, a little bit mu k, it says choose the most likely one. So basically, in a hard way, it splits the points into the mu's and then re-estimates. The only difference is that basically these are only ones and zeros. Right? I committed to what is the label of each point. And in the general EM algorithm, I'm not committing. I'm splitting the point, or I'm representing a probability distribution over the mu i's for each point. Okay? Clear? And this is really the same thing everywhere, right? So this is going to be, this is the same thing with the coins, and this is the same thing with other more complex models where you have, you can choose whether you want to run this EM and maintain a probability distribution over the hidden variable at each stage. In this case, this is the probability distribution you maintain over the hidden variables. Or you just commit and you say, it's here, it's there, and so on. Questions? What was the question? Yeah? You can compute the same algorithm in matrix operations, if that's what you're asking. But you cannot derive a closed form for this. The computation itself, you can write it as a matrix operation. Yeah. 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 And also of k, right? So, but in fact, you could incorporate sigma into your model and as another hidden variable. And in fact, you could also include k if you wanted. I'm just not doing it here because I want to use a simple model. And in practice, it so happens that definitely for k, people don't do it. They don't do EM over k. They sometimes do search over k. But they don't plug it into the algorithm. And sigma, sometimes people do. But in practice, but in everything that you can model, you can include as a hidden variable. Okay. Okay, so this is just another comment here. If you want to think about it geometrically, really, this algorithm finds the best k-means in the sense of minimizing sum of square distances. Very easy to see, yeah? What happens if? Cannot be. At least one of these has to be 1. So the Zij were defined in such a way that it's the probability of I coming from J. Okay, so just to summarize, so what we've done is we talked about EM, general algorithm. We gave 2 examples of how to use it in order to estimate the most likely density function, probability distribution, for a mixture of probability distribution. As I said before, it's known to converge to a local maximum of the likelihood function, and therefore you will need to restart. It depends on assuming a family of probability distribution, and really it's quite useful in practice. So it's a good learning algorithm, of course, as a function of how good is your guess. Or assumption of what is the family of probability distribution that you're working with. Okay, so let me give one final example that will hopefully get you to think about this last point. And again, I want to link it to stuff that you already know. So let's assume I have the following learning scenario. I have a training set, a sample of data points, and I'm thinking about my data points as n plus 1 dimensions. Okay, x0 up to xn. Let's say Boolean. Yeah, it's 0, 1 to n plus 1. Eventually, your task is to predict the value of x0 given x1 up to xn, right? So this is your training data. And in the future, I'm going to give you just x1 to xn and ask you predict x0. So how would you want to model it? Now you're experts in machine learning. What are you going to do? Okay, I'll give you a hint. Let's assume I would have asked you this question 3 weeks ago. What would you have done then? Yeah, so you would think about x0 as a label, erase it from there, call it L, and now all you have here is a bunch of training data and dimensions with a label L. And in the test, of course, I'm going to give you just the example. Without the label, predict the label. Okay? Do you agree that this is what you would have done 3 weeks ago? Yeah?
Do we know any about actually, do we know any values of x0?
Values of what?
X0.
Everything is 0, 1 to the n. Everything is Boolean here.
Okay, but we want to.
No, I gave you training data.
Oh, okay.
This is the training data. Training, a sample of data points, x0, x1, up to xn. So a month ago, I would have written it as L, comma, x1 up to xn, right? Or y, comma, x1 up to xn, and everything would have been fine, right? So it would be clear that the first coordinate is the label, and the rest are the features. And the question is, train a model. So what would you do with this hint? How would you learn it? Yeah. Choose your favorite learning algorithm. You have no idea what the data is. Where is the you can do decision trees. Again, X0 is the label. You can do perceptron. You can do SVM. Do whatever you want, right? But it's just the standard supervised learning model. That's has to be clear. If it's not clear, let's make sure that it's clear. You agree that this is just, I'm cheating you here because I'm calling this X0 and confusing you a bit. But it's just the standard supervised setting. Okay, so this was 3 weeks ago. Now I think we have more options. And this will allow us to think a little bit more about EM and kind of placing it. So now I'm going to assume that I have a model of how this data is being generated. Right? For the standard supervised learning setting, I had no model. I just said, oh, here's labeled data. I'm going to run my learning algorithm. I don't care and don't want to know how the data was generated. Now, I have other tools. Maybe I do know how the data was generated. And let's assume that the data was generated this way. So there is some hidden variable, z. It's hidden. You didn't see it, right? That's exactly what the meaning of hidden is. Z, it takes k values with probability alpha z. So it's alpha 1, alpha 2, alpha k. They sum to 1. With probability alpha 7, the probability z takes the value 7. Okay? As a function of the value z, the hidden variable z, I'm generating the xi's. And I have some probability distribution, piz. How do I generate? So once z is 7, I have n plus 1 probabilities, p0, 7, p1, 7, and so on, to generate the xi's. So this is the picture that you should have in mind, right? So first of all, I choose z. I choose z with probability alpha z, either 1 or 2 up to k. Once I chose z, I'm generating x1, x2 up to xn. Sorry, it should be start with 0 up to xn with this probability, piz. Okay? Clear how I generate the data? It's almost like the coin, where I choose coin 1 or coin 2, but when I chose the coin, actually, all the tosses came from the same p. Now I say the first coin, the first toss coming with this probability, the second from this, and so on. So it's a little bit more complex, but it's the same idea of a model. First choose the z, or the coin name, and then toss. Yeah? No. Unrelated at all. This is the problem. This is the problem. Two options. One, supervised learning. No assumptions. Just take your black box algorithm and run. Two, someone gave you a hint. You know what? Actually, I think I know how this data was generated. This data. It was generated. There is some cause. There's some hidden cause. A day in the week. Every day, different data is generated. If it's Sunday, we generate data this way. If it's Monday, we generate the data this way. If it's Tuesday, we generate data this way. Only that you don't know when you look at the data what day it was generated in. So this is Z. Okay? So I'm just assuming it, doing nothing. So I'm assuming this model. Okay? Is it clear what the model is? Now, with this model, you have another option. You can run EM, estimate the parameters. What are the parameters? The parameters are the alphas and the PIZs. Once you have all the parameters, and I give you x1 up to xn, if you think a little bit about it, you'll see that you can actually compute the most likely value of x0. Yeah? Okay, so that's exactly the question. The question now is we have a comparison, right? It's one setting, and you can ask yourself which is going to work better. The one that I knew a month ago or the one that I know today when I know EM. And this is exactly where I was getting to. So first of all, I want to make sure that you know that you have these two options. One we're going to call parametric. We assume a way in which the data is generated. These alphas, these p's, and we can run EM. Of course, to run EM, we had to make these assumptions. And the non-parametric, just learn x0 directly as a function of other variables. In both cases, we have to make some assumptions, right? In the parametric, we have to assume how many values can z take? We assume k. And what are the probability distribution? Let's say we assume binomial. In the non-parametric, we assume something about the expressivity. Can we use perceptron? Can we use perceptron just with the x1 up to xn? Should we conjoin them? Should we use kernels? Should we use other things? But we know how to learn, given these assumptions. Okay, it turns out, and I'm not showing it, but it's a little bit of algebra, that if it so happens that k is equal to, so the z variable can take only two variables, this function, x0 is a function of x1 to xn, is actually a linear function. So you actually can make a fair comparison between parametric and non-parametric in this specific setting. It's often very difficult to make good comparison between these two frameworks. But under this assumption, you can make a good framework. So what happens is, I think your intuition is just about right. It so happens that if you know k, and you tell your model k is 2, or even if you tell your model k is 5, and the data was really generated from 5, EM is going to win. On the other hand, if you don't know k, that is, you tell your algorithm, I think that k is 2, and k actually is 5. The data was generated with k equal 5. The linear algorithms are going to perform better, which I think is a very interesting issue from your perspective. First of all, to understand, and go over it again to make sure that you understand that from the way I describe the problem here, you have a lot of options now. If you know more about the problem, you have less options, but you can win, right? So you can get better learning here. And this is really the bottom line. The bottom line is that EM is doing really, really well if you know the model or the family of models, and you can beat it in case it doesn't. Okay, let me finish here. Final quick question. Yeah. Yeah, it's unfair, right? I know something about it, but as I said, for the case equal 5, you're right. For the case equal 2, it's actually a linear function. So for the case equal 2, it is a fair comparison. And you can see that for the case equal 2, in fact, the results are quite comparable. Yeah. Okay, have a nice weekend.
Doing a paper,